This is the second lecture in a series of lectures covering first-order systems and their solutions. In the first lecture, we didn't actually solve or find the solution to any first-order system, but we did formulate the state equation for a first-order RC and a first-order LR circuit. And we also kind of explored how to think about the state equation, how to interpret it. We wrote an approximate discrete time solution, or at least a finite difference equation that could be put into a spreadsheet or into a program to simulate numerically the solution to a first-order system. But we actually never solved the first-order system. So that's what we're going to do now. So we're going to use as our case study this simple RC circuit, okay, driven by a voltage Vs and having a response, we'll say Vc, the voltage across the capacitor. Okay. Now let's suppose that suppose Vs is equal to 10 volts, just a constant voltage. Okay, and let's suppose that the capacitor voltage at time 0 is equal to 0 volts. Okay, so before we go into analyzing this, let's just think about, intuitively what happens. We've got 10 volts on the left side, and on the right we have a capacitor that has 0 volts across its terminals. So if you do KVL around the loop, it's obvious that the 10 volts from the source are applied completely across R, and there is a current that will flow from the source to the capacitor that's equal to the 10 volts over R. Okay, so we can say this is 1K, and so that means we'd have a 10 milliamp current flowing into the capacitor, which means that the capacitor will charge, right? The capacitor will charge, the voltage will increase on it. We saw this from the state equation. Let me actually write the state equation so we can reference it here. We had Vc, dVc dt, and actually tau times that, which tau was defined as R times C. Okay, so tau dVc dt plus Vc is equal to Vs. We also wrote this as Vc dVc dt equal to 1 over tau times Vs minus Vc. All right, that was our state equation. So again, if the voltage initially on the capacitor is 0 volts and you apply 10 volts at Vs, the right side of this state equation is going to be 10 volts over tau. Let's assume that tau is, we'll say that tau equal to Rc is equal to 0.1 seconds, okay? So we'd have 10 volts on the right side, 10 minus 0 divided by 0.1, so we'd have 100. 100 volts per second is the value of dVc dt. So at time 0, when this first starts out, the voltage across the capacitor will start rising at 100 volts per second. So not long, immediately after the voltage starts rising on the capacitor, you no longer have all 10 volts of Vs across the resistor, right? You have Vs minus Vc, so you have a little less than 10 volts. And what that will do is it'll result in a slightly less current going in and charging the capacitor. And as this progresses, there will be a decreasing rate of charging as the capacitor voltage goes up to 0. So let's ask the question of when does the capacitor cease to charge? Right? When does the time rate of change of the capacitor voltage go to 0? Right? So when does dVc dt equal 0? Right? And the answer is right above here. It's going to be when Vc is equal to Vs. That's pretty apparent from the state equation, right? Because it's when the right side is equal to 0. So if we were going to plot, so therefore we can say just already surmise what the response is going to look like. If the capacitor voltage starts at 0 and it's ultimately going to reach Vs, so 10 volts, all right, it's going to have some kind of a exponential rise. Okay, it'll look like this. So now before even solving the equation, diving into the math of it, we can already we can critique what we find based on what we now understand intuitively about the circuit. The voltage is going to rise from initial voltage, in this case we've said 0 initially, up to Vs. And once it gets to Vs, because dV dt then is equal to 0, once it gets to that state, it'll stay there because the capacitor voltage no longer changes with respect to time. So I want to point out there are two elements or two components to this response. One of the components is the final value of where the capacitor voltage settles out at. Okay, that response is called the steady state response. It occurs somewhere way out here. Steady state response. All right, that is, theoretically, it's at t equal to infinity. All right, we could say that it's going to take infinite time before the capacitor voltage asymptotically, actually reaches Vs. Right, because the closer it gets to it, the smaller the right side of our state equation, the shallower or the smaller the time rate of change of capacitor voltage, and so it slows down as it approaches its final value. So that's the steady state. The other part is this, call it this transient. Okay. Now I'm showing this as kind of having this discrete dividing point in time where the transient stops and the steady state begins, but that's false. I mean, in practical terms, we can say that after a certain amount of time, the response, the capacitor's voltage is essentially, as far as we can detect, at Vs, but theoretically it never gets there until time infinity. But what this points out is that there are two elements to our response. There's what we call a steady state response and a transient response. We'll also use terms of saying that there's a particular response, okay, particular to the type of forcing that we're applying to the system. In this case, the forcing is a 10 volt voltage for Vs. And there's a homogeneous response. So let me write these. There are two, because there's several terms here that'll get confusing. So there are two components to our complete response Vc of t. Okay, the response that I showed here, that I plotted out on the right. Okay, one, there is a steady state. We'll use several terms. Steady state, or a particular. This is more a mathematical term. In a math class, they'll talk about the particular. Particular, or even we'll call it a forced response. Okay, why would we call it forced? It's because we can think of Vs, the external, the independent source in the circuit, is forcing, it's imposing itself onto the circuit, and the circuit responds to that forcing. Okay, and then secondly, there is a transient. Okay, transient or homogeneous, or we also call it a natural response. Okay, these are all kind of interchanged. So think of the first one is the final value of where things settle out at. And the second one is how you get from the current state, the starting state, to that final value. Do you get there quickly? Is it really sluggish? Does it go quickly and actually go past the final value and then come back down and oscillate around about the final value before it settles out? That's all captured in this transient or homogeneous or natural response. Okay, so let's look at the particular or steady state or forced response. So we'll say particular, I'll call it particular response. And we'll call it Vc of P. Okay? Where we're going to define Vc of t, the complete response, as the sum of the particular response plus the homogeneous or transient response. So we're going to put both of these together. Okay, and this is what you'll always do when you solve a differential equation, whether it's first order, second order, etc. So in the particular response, we're going to look at satisfying the full differential equation as it stands right now, which is the tau Vc dot, okay, and I'll say Vc of p plus Vc of p is equal to Vs, where Vs is a constant. Okay, and so we're going to guess at a solution, all right? But as a guide, what we'll use as a guide is try VCPs that are of the same form as Vs, okay, the driving, the forcing signal. Sometimes you might consider integrals of Vs or derivatives of Vs, okay? But at most, it will be, either of the form of Vs or an integral of Vs or a derivative of Vs. Most of the time, it's just of the form of Vs. So in this case, Vs is a constant, right? We're going to just have Vs is equal to 10 volts. So let's try Vc of p equal to some constant V, we'll just call it Vp, okay? A constant. And we'll plug it in. So plug in and test it. So when we put it into the differential equation, we'll get tau times the derivative of a constant is going to be 0, right? Plus that constant is equal to Vs. Well, lo and behold, we can satisfy that if we choose Vp to equal Vs. Okay, that's our particular solution. So therefore, Vc of p is equal to just Vs in this case. Quite trivial. This is a trivial example. Yeah. All right. So we have our steady state solution. In fact, we haven't really discovered anything new. We already found back here that that was going to be the case. Okay, now we need to find how does the system move from an initial condition to that steady state value. So we need to find what we call the homogeneous response. Homogeneous response. We'll say VCH. Okay, now in this case, we are not looking at how the system responds to Vs being there. So in fact, we're going to turn Vs off. Turn Vs off. So in other words, Vs is going to be 0. So that results in the homogeneous, what we call a homogeneous equation, okay, which is our initial state equation or differential equation, but with the right side set equal to 0. So tau dVc dt plus Vc is equal to 0. Okay. So now look at what we have here. We essentially have, we need to find a function, and I'll say with Vc of h, Vch. Okay. We need to find a time function, Vch, that when you take the derivative of it and then add it to the original function and weight it by tau, you can actually have the sum equal to 0. Okay. So some things that clearly would not work. For instance, if you had a Vc of h that was, so let's think of some possible solutions. Okay, so for instance, if Vc of h of t was equal to some constant times t, t squared, let's say, all right, then we'd have tau times 2kt plus kt squared is equal to 0. The question is, can that ever be equal to 0? Well, you could have a trivial case where k is equal to 0. That's useless. But because one of the terms depends on time linearly and the other term depends on time to the squared, to the second power, these can never be equal. So this is not a valid solution. Okay, what we need is something that when you take the derivative, you get the same functional form back. Well, there's a function that actually has that characteristic. So if you consider the function, let's say, a to the x, okay, then if you take the derivative with respect to x of a to the x, you'll get log of a times a to the x. And if a is chosen to be equal to the natural number e, then we would have the case where the derivative with respect to x of e to the x is simply equal to log of e, which is 1, times e to the x, right? So the derivative of e to the x gives you e to the x. That's precisely the type of function we want. Now, what we're going to write this a little more generally. Let's try VCH of t equal to some constant, we'll call it a, times e to the, and then instead of just going t, let's say e to the st. We'll call it e to the st, where s is some constant. Okay, let's just try this out. And the reason I'm putting an s in there is because I'm remembering that we're not solving the equation of derivative of VC with respect to time plus VC is equal to 0. We're solving the case where the derivative is multiplied by tau. So I need to have a little bit more flexibility in the solution that I'm picking. E to the t would not be sufficient. I need an e to the some constant times t, and that's why I'm going to use s. So let's just see. We'll try it. We'll see if it works. So when we take the derivative, we'll have tau times s. When we take the derivative of e to the st with respect to t, we'll get s e to the st. Okay, a still is in there. Okay, plus vc of h, which is e to the st, and that's all equal to 0. Well, we can collect some terms where we have tau times s plus 1, all of that times a e to the st is equal to 0. So, except for the trivial case where a is equal to 0, which would be pretty useless, we can satisfy this equation when s is equal to, when this term here is equal to 0, or in other words, s is equal to minus 1 over tau. So therefore, we have a solution here. Vc of h of t is equal to a times e to the st, where s is minus 1 over tau. So we have e to the minus t over tau. Okay, and what does this look like? It's an exponential decay, assuming tau is positive and assuming that a is positive. Here it starts from a positive value and goes to 0. Okay, so therefore we have a homogeneous solution here. What this tells us is, how does this system change from one state to the next? It changes by way of an exponential function where we say the time constant of that exponential function is equal to tau. And tau, of course, in this case we found was RC. So we can also write this as a e to the minus t over RC. Okay, so we have the particular solution, we have the homogeneous solution. Now we want to write the complete solution. Write the complete solution. Okay, so we have VC of t is equal to VC of p, the particular solution, plus VC of h, the homogeneous solution. And that's going to be Vs, because that's what we found for the particular solution, plus some constant that we have not yet determined, a, times e to the minus t over tau. Okay. Now, to finish this up, we need to be able to pick what a is. And to do that, we need to consider what the starting point or the initial condition of this the capacitor is. So we had said that Vc at time 0 was equal to 0. Okay, I'm going to call that voltage VO, all right, in this case, but then we'll be more specific, okay, and let VO equal to 0. Okay, so if we have at time 0 VC is equal to VO, then we would have VC 0 equal to VO is equal to VS plus A times e to the minus 0 over tau. Okay, so this will just be 1. So now we can solve for A. A is going to be equal to big VO minus VS. Okay, so now we can write our complete solution. VC of t is equal to VS plus the quantity VO minus VS times e to the minus t over tau. And this is going to be valid for all time greater than or equal to 0. Okay, and in the case when VO is equal to 0, we would have VC of t is equal to quantity VS, or VS times the quantity 1 minus e to the minus t over tau. All right, what does this look like? Okay, 1 minus e to the minus t over tau, it evaluates to 0 at time 0 and evaluates to 1 at time infinity. So this is going from 0 up to an asymptotic value of Vs, just as we surmised or intuitively determined at the beginning when we were just looking at the circuit and prior to writing an equation. So this is good news. So our solution does support what we understood the circuit to exhibit in terms of its response to a constant voltage Vs. Okay? So this is the complete solution to a first-order system, and we have found the complete solution by first looking at the particular response, or the steady-state response of the system, and then at the homogeneous response. Okay? Now, it may, just some things to think about. Notice that when you, if you find that the particular solution, being Vs this time, is a solution to the differential equation, which it was, we found that, then if you take that particular solution and you add the homogeneous solution, the combination of the two is still a solution to the differential equation. The reason is that when you plug in the homogeneous solution, the left side of the differential equation, tau times dVc dt plus Vc, all of that evaluates to 0. So it doesn't disturb the equality that was achieved when you plugged in just the particular solution. Okay, so that's why we can have a complete solution that is the sum of the particular and the homogeneous, and that still satisfies the total differential equation, or the full differential equation with Vs being there. So I will pause here, and then we'll pick it up in another lecture to carry this a little bit further.